Have you ever stopped to think about the invisible pathways that power our modern world? You know, the ones carrying all the data for traffic lights, emergency services, everything that keeps things moving.
It's easy to just assume they're there, right? But the complexity behind them, especially their design and installation, is pretty amazing.
Absolutely. And today we're diving deep into that. We're actually getting an exclusive look at how these vital communication pathways are designed and built for Florida's own transportation network.
Exactly. This isn't just some generic overview. This material comes straight from the experts at AtkinsRealis, developed specifically for the Florida Department of Transportation, or FDOT. It's part of their Intelligent Transportation System Masterclass.
So we're leveling up today. Think Fiber Optics 103, really getting into the nitty-gritty beyond just the basics.
And you'll notice as we talk, we'll point out specific things from FDOT documents, like their standard plans and specs. In the original AtkinsRealis materials, these were flagged, showing you exactly how these ideas get put into practice right here in Florida. Super relevant stuff.
Okay, so before we jump into the deep end, let's just quickly touch base on some basics we've covered before. Things like, the cables themselves, splice enclosures, patch panels.
Right. And the two main ways fibers get connected. There's splicing.
Which is like fusing them together with heat.
Exactly. A permanent join, very low signal loss. Then you have terminations, where you actually put a physical connector on the fiber end so it can plug into equipment like a switch.
Got it. Splicing and termination, those are the building blocks.
Totally. And beyond just the types of cable, like multi-mode or single mode, there are really four main jobs or functions that fiber optic cables do in a network. Thinking about them this way helps organize everything.
And the best way to picture these functions is actually by comparing them to something familiar, our roads.
It's a great analogy. It really clarifies how the network is structured. So the first one, the big one, is the backbone, sometimes called a trunk line.
Okay, so the backbone is like the interstate highway.
Precisely. It's got the highest fiber count, usually, carrying the most data between your main hubs, think your Regional Transportation Management Center or TMC. It's the most direct, high-speed route, no stops.
Makes sense. Interstate? Then what's next?
Next level down is distribution. Think of these as your arterials, like State Road 50 or maybe 436 here in Florida.
Okay, so they branch off the main interstate.
Yeah, they branch off the backbone. They connect out to multiple field devices, and they help kind of segment the network. Now, what's interesting for FDOT specifically is that sometimes their backbone and distribution cables do pretty similar jobs. That line can be a bit blurry compared to, say, a regular telecom network.
Huh, interesting. So it reflects the specific needs of transportation systems.
Exactly. Then, going smaller still, you have drop cables.
Ah, so these are like the local roads, or maybe even the driveway to your house.
Perfect analogy. Local roads, or maybe a cul-de-sac, they provide that direct link from a distribution line right to an individual field device, your camera, your sensor, whatever it is. Usually the smallest cables in terms of fiber count.
Okay, backbone, distribution, drop. Is that it?
There's one more, a bit more specialized, the spur.
A spur. Like a private road, maybe?
Exactly like a private road.
Yeah.
It's basically a point-to-point link between two specific field devices that might not have a direct network connection otherwise. It kind of cleverly piggybacks off an existing connection, maybe saving on extra splicing or digging. It's a smart engineering solution you see Atkins-Realis use for FDOT sometimes.
Got it. So four main roles: backbone, distribution, drop, and spur. That really helps visualize the layout. Now, how does the data actually flow on these? We touched on simplex and duplex before.
Right. Simplex is just one-way traffic. One fiber, transmit only TX. Think of a simple broadcast.
Like a one-way street. But for ITIS, you need cars going both ways, right?
Absolutely. For intelligent transportation systems, you almost always need duplex. That's two-way simultaneous communication. It needs two separate fibers. One to transmit, TX, and one to receive, RX.
So like a normal two-way street, that makes sense for devices needing constant communication.
It's the standard for IT's deployments because you need that constant dialogue, that real-time back and forth.
Okay, so if duplex is the norm, what happens if you just connect devices in a straight line? Like node A talks to B, B talks to C, C talks to D, a simple daisy chain.
Well, it works until something breaks.
Ah, so if the connection between, say, B and C gets cut, maybe a construction accident.
Then everything downstream, like node D in your example, completely loses communication with A and B. That link between B and C becomes a critical single point of failure.
And for something like traffic signals or emergency messaging, that's That's bad, really bad.
It's unacceptable, really. You can't have the system collapsing because one cable gets nicked. That single point of failure is a huge vulnerability.
So how do engineers like the folks at AtkinsRealis working for FDOT get around that? How do you avoid that nightmare scenario?
The answer is redundancy. It's absolute fundamental. It's all about creating multiple paths for the data to travel between points on the network.
Multiple paths, so like building detours.
Sort of. More accurately, you typically create a ring or a circular pathway. If the main road gets blocked, the traffic could just go the other way around the circle. It ensures communication keeps flowing, even if one path fails.
Okay, a ring makes sense. So data can go clockwise or counterclockwise, basically.
Yeah. Essentially, yes. You effectively have two rings for bidirectional flow, ensuring that even with a break, everything stays connected.
How do you physically build that redundancy? Are there different ways?
There are two main approaches. The first, and maybe the most robust, is physical separation.
Okay, what does that involve?
It means installing completely separate cables, often in different conduits, maybe even on opposite sides of the road. You saw this in massive FDOT projects like the I-4 Ultimate Rebuild. Same nodes get connected, but via physically distinct routes.
Wow, that sounds incredibly secure. Like a backhoe hitting one conduit wouldn't affect the other one at all.
Exactly. The security against physical damage is the huge plus. But
There's always a but. I'm guessing it's expensive.
very. More materials, more digging, more infrastructure. And ongoing operations and maintenance costs are higher too. It's a trade-off FDOT has to weigh based on how critical that particular link is.
So what's the alternative if you can't physically separate everything?
The other common method is using multiple circuits but within the same physical cable.
Ah, okay. So you use different pairs of fibers inside that one cable sheath. One pair for the main path, another pair for the backup.
Correct. The big advantage is cost less infrastructure, less labor. Much cheaper to implement.
But the downside seems obvious.
Yeah, if that single cable gets physically cut, both your primary and elementary paths go down. You still have logical redundancy, but you lose the physical protection. So again, it's a risk assessment that AtkinsRealis helps FDOT make.
Right. Different levels of protection for different costs and risks. Okay, let's get practical. Say we need to build one of these redundant rings. This is something AtkinsRealis designs for FDOT all the time, right? Let's imagine connecting two hubs, Hub A and Hub B, through a few intermediate nodes, say node A, B, and C. And our primary circuit needs to use specific fibers, maybe 63 and 64.
Okay, a very typical scenario. First, just a couple of quick reminders. One, fiber uses light, and light needs a continuous, unbroken path. Any break, any gap means data loss.
Got it, continuous path.
Two, we find specific fibers using the standard color code for buffer tubes and the fibers inside them. So fiber 63 and 64 would be the green and brown fibers within the white buffer tube.
Okay, white tube, green and brown fibers. So where do we start physically building this connection out in the field?
You'd start at the splice vaults or enclosures for each node, like node A. That main backbone cable, the trunk line running past, gets carefully opened. Fibers 63 and 64 are located.
And then you cut them?
You carefully cut those specific fibers. Then you take the drop cable, the one going up to the node A cabinet, and you fuse or splice the corresponding fibers together. So the path that was going straight along the backbone now takes a turn upwards into node A.
Ah, okay. So the light traveling on 63 and 64 gets redirected up to the equipment at node A.
Precisely. Now, once that drop cable reaches the cabinet at node A,
what happens there? Just connect it straight to the switch.
well, best practice, especially for FDOT work advised by AtkinsRealis, is to terminate the entire drop cable onto a patch panel first, usually in groups of 12 fibers.
Why terminate all of them if you're only using a few right now?
Future-proofing and maintenance. It makes it so much easier to test, troubleshoot, or add services later without having to re-enter that splice vault down below. It's all neatly presented on the panel.
Okay, that makes sense. So fibers are terminated on the panel. Then what?
Then you use short fiber optic jumpers. You'd connect, say, the first pair on the panel, blue and orange, maybe from the drop cable side to the port on your Ethernet switch. That sets up one direction of the duplex link.
And for the other direction, the receive path.
You use another jumper, maybe connecting the next pair, green and brown, to establish the opposite direction. Now you have full two-way communication transmit and receive between the backbone and the switch at node A. The switch can now talk both ways along the main path.
And you just repeat that same process at node B and node C.
Yeah.
Cut the backbone fibers, splice to the drop, terminate the drop, jumper to the switch.
Exactly. You replicate that pattern at each intermediate node. That builds out the primary path, that sort of daisy chain connection along fibers 63 and 64.
But that's just the primary path. We still need the redundancy, the ring. How do we close the loop and add the backup?
Right. So at the main hubs, Hub A and Hub B, you handle things slightly differently. At Hub A, you connect that primary circuit, fibers 63 and 64, into the main switch there. But then you activate the redundant path.
Oh, using different fibers.
Yes. You pick another pair in the backbone cable, maybe an odd pair like fibers 71 and 72 that's rose and aqua in the next buffer tube. You connect these fibers to the switch at Hub AA as a secondary path.
Okay, so Hub A has connections for both the primary 6364 and secondary 71 and 72 paths. What's special about 71 and 72?
What's crucial is that fibers 71 and 72 don't get cut and spliced at the intermediate nodes, ABC. They express right through those splice faults. They just pass straight by, continuing directly towards Hub B.
Ah, so the backup path is like an express lane, bypassing the local stops.
Exactly. Then finally, at Hub B, you connect both pairs. You connect the primary 63 and 64 coming from node C.
Right.
And you connect the secondary 71 and 72 coming directly from Hub A. You might need to flip the transmit and receive pairs logically at Hub B to complete the circuits properly, closing that collapsed ring.
Wow. Okay, let me picture this. Data can go Hub A, Node B, Node C, Hub B on fiber 6364. Or if there's a break, it can go Hub A, Hub B directly on fibers 7172. And presumably data can flow the other way too.
Precisely. You've created that redundant loop. It's a foundation for, I'd say, 95% of reliable fiber optic networking like FDOT requires.
That clicks, but you mentioned earlier, designing this is one thing, dealing with what's already in the ground is another.
Oh, yeah. That's often the biggest headache, and where AtkinsRealis' field experience for FDOT really comes into play, dealing with existing conditions.
Because the documentation isn't always perfect, or even there.
You got it. Cabinet logs are usually pretty good, you know what's plugged in where, but splice records out in the field, those can be patchy or missing altogether. You might have as-built plans, which are essential, but sometimes you literally have to trace fibers or, call up the local network admin, the Shane Owens of that district, who just knows how things were connected years ago.
Sound like some real detective work sometimes.
It absolutely can be. You have to marry the design plans with the often messy reality on the ground.
Okay, so moving on from the physical layout, let's talk about signal quality. You mentioned loss earlier. Link loss, that sounds important.
Critically important. Link loss is basically the total amount your optical signal degrades or weakens from the transmitter to the receiver. It's measured in decibels, dB. Too much loss, and the signal becomes unreadable.
What causes that loss?
Several things contribute. First is just the fiber itself, attenuation. Light naturally gets dimmer the further it travels through the glass. It's like looking at stars, the farther away they are, the dimmer they seem. We measure this in dB per kilometer. Standard specs exist, like from AtkinsRealis, but you always want the actual value from the cable manufacturer's sheet for real design.
Okay, so distance causes loss. What else?
Every connection point adds loss. Splice loss happens where two fibers are fused. Industry standards might allow up to 0.3 dBs per splice. But here again, FDOT, working with AtkinsRealis, demands much, much better.
How much better?
FDOT specs often require only 0.05 dBb max for new-to-new fiber splice, maybe 0.1 dBb for splicing new fiber to an existing one. That's incredibly tight.
Wow, okay. And the other connection type? Terminations.
Yep, connector loss. Where the fiber plugs into a patch panel or equipment, wtih might say 0.75 dB is acceptable. FDOT. They'll want something like 0.3 dB for factory polished connectors and maybe 0.5 dB max if it's terminated by hand in the field.
So across the board, attenuation, splices, connectors, the FDOT standards are significantly tougher than the general industry ones.
Massively tougher. And it's intentional. AtkinsRealis designs to these standards for FDOT because it builds in a huge safety margin. It ensures the network isn't just functional on day one, but stays reliable for years, even decades, as equipment ages or data needs increase. It minimizes future truck rolls and downtime for critical infrastructure.
That makes a lot of sense. Invest in quality up front. So you add up all these potential losses, attenuation over distance, loss from each splice, loss from each connector.
Plus, you always add a little safety margin, maybe 2 or 3 dB just to be safe. That total gives you your calculated link loss.
And then you compare that number to the power budget. What's that exactly?
The power budget, or optical budget, is simply how much loss the equipment can handle. It's the difference between how strongly the transmitter sends the light signal and how weak a signal the receiver can still understand.
Where do you get those numbers?
Straight from the manufacturer's datasheet for the specific equipment, like the SFP transceiver module you're using. It will list the minimum transmit power and the receiver's sensitivity. subtract sensitivity from transmit power, and that's your budget.
Okay, so the calculated link loss must be less than the power budget for the link to work reliably.
Exactly. But it's also important the signal isn't too strong. Too much power can actually overwhelm or even damage the receiver. So the received signal needs to fall within a specific window.
Let's try that example calculation you mentioned, the AtkinsRealis one for FDOT. A 14.5-mile single-mode run, 3 splices, patch panels at both ends, 100 megabit SFPs, and a 3 dB safety factor. Is it feasible?
All right, so first step, identify all the loss points. 14.5 miles is 23.4 kilometers. We have 3 splices and connectors. Well, patch panel at each end means a connector pair there, plus the jumper to the SFP at each end. So that's actually 3 connectors per end times 2 ends equals 6 connectors total.
Okay, 23.4 kilometers, 3 splices, 6 connectors. And we use the FDOT loss values for those splices and connectors, right? Not the looser industry ones.
Absolutely critical. You plug those stricter FDOT numbers into the formula, length attenuation kilometer, plus hashtag splices FDOT splice loss, plus hashtag connectors FDOT connector loss, plus safety margin.
And doing that math for this scenario gives us...
Using typical FDOT values and that 3D billing margin, it comes out to a calculated link loss of about 20.1 dB.
20.1 dB of loss. Now, what's the power budget from the SFPs?
Let's say a typical 100 meg SFP has a transmit power around -14 dBm and a receiver sensitivity of -34 dBm. The difference, -14 minus -34, gives us a power budget of 20 dB.
Uh-oh. So the calculated loss is 20.1 dB, but the budget is only 20 dB.
Exactly. The link loss is greater than the power budget. So based on this calculation, this specific design is not feasible under FDOT standards. The signal would likely be too weak by the time it reaches the receiver.
Wow. So that design calculation, using FDOT's tough standards, tells you before you install anything that it won't work reliably.
Precisely. It forces you back to the drawing board. AtkinsRealis would then look at options. Can we use SFPs with a better power budget? Can we redesign the route to eliminate a splice? Do we need to add an amplifier or regenerator somewhere in the middle? It's a crucial check. And remember, FDOT's actual field testing requirements after installation are often even tighter, giving yet another layer of quality assurance.
Okay, design's feasible now. Let's get that cable in the ground. 2 main ways, you said. Pulling and blowing.
Right. Pulling is the traditional method. You literally pull the cable through the conduit using its internal strength member. You clear the conduit, attach a pulling grip securely to the cable's strength core, never the glass itself, attach that to a pull rope or tape already in the conduit, and then apply force using lubricant, guiding it carefully through pull boxes.
It sounds straightforward, but maybe labor-intensive.
It can be. And there's always a risk of exceeding the cable's maximum pulling tension or bend radius if you're not careful, which can damage the fibers. Distance is also a limitation.
So what's the alternative? Blowing.
Yeah, cable blowing or jetting is more advanced. It uses high-volume compressed air. You attach a small piston or carrier, sometimes called a rat or missile, to the cable end. The air pushes this carrier, which in turn pulls the cable along, while the airflow itself creates drag forces along the cable jacket, effectively floating it through the conduit.
That sounds faster. Gentler on the cable.
Generally, yes to both. You can often install much longer continuous lengths, sometimes thousands of meters, much faster than pulling. And because the cable's mostly floating on air, there's less friction and stress on it.
Any downsides to blowing?
The main one is conduit integrity. The conduit system has to be pretty much airtight. No significant cracks or leaks for the air pressure to work effectively. It's also possible, though tricky, to blow new cables into conduits that already have older cables, but the contractor takes on the risk if they damage the existing ones.
And FDOT has specific rules for the conduit system itself, right? Like pull box spacing.
They do. AtkinsRealis designs factor these in. Generally, it's pull boxes every 1,700 feet or so in rural areas, maybe closer like 1,500 feet in urban settings.
And slack loops. I hear about needing extra cable.
Yes. That's crucial for future repairs or modifications. FDOT typically requires about 50 feet of slack cable, coiled in each pull box. And at splice points, you need 100 feet of slack from each cable entering the splice. So for a backbone to drop splice, that's 100 feet from the backbone, 100 feet from the continuing backbone, and 100 feet from the drop, 300 feet total coiled nearby.
Wow, that's a lot of extra cable. And bend radius, too.
Always critical. You can't bend fiber too tightly, the signal escapes or the glass breaks. FDOT specification 633 defines the minimum bend radius, often something like 14 times the cable's outer diameter when it's under tension. And one more FDOT rule, no direct burial of fiber. It must be inside a conduit for protection.
Okay, fibers installed, spliced, terminated. Now, the moment of truth testing, how do you verify it meets those tough FDOT specs?
The primary tool for that is the Optical Time Domain Reflectometer, or OTDR,
That sounds fancy.
and expensive.
Very fancy. And yes, quite expensive. A good OTDR machine can run you like up to $15,000, but it's essential for quality control.
How does it work? What does it actually do? Basically, it shoots a pulse of laser light down the fiber and then listens for reflections, or echoes, coming back. It uses the timing and strength of these reflections based on the known speed of light in glass fiber to map out the entire fiber run.
So it can see things along the fiber.
Exactly. It sees the gradual signal loss from attenuation. It sees events like connectors, which cause a noticeable reflection spike. It sees splices, which usually show up as a small drop in signal with very little reflection. It can pinpoint breaks or sharp bends. It measures the loss of each event and the total loss for the link.
So you get this graph, this trace. How do you read it?
Well, a steady, gentle downward slope is normal. That's your attenuation, the loss over distance. A sharp spike upwards followed by a drop usually means a connector, high reflection, some loss. A small, distinct drop with almost no spike is typically a good splice, low reflection, minimal loss. Any weird bumps or big drops might indicate a problem, like a bad splice or a cracked fiber.
And for FDOT projects, this testing is mandatory and has to be documented.
Absolutely. FDOT Section 633 lays out the testing requirements. The contractor performs the OTDR tests, usually with an FDOT construction inspector present, and submits those traces and results to FDOT for review and approval. It proves the installation meets those stringent standards we talked about.
And those FDOT testing standards for loss are super tight, right? Even tighter than the design calculations.
They are. For instance, the allowable attenuation per kilometer is often specified even lower for testing than for design, maybe 0.35 dB kilometers at 300 and 310 nanometers, 0.25 dB kilometers at 1550. Connector loss might be capped at 0.5 dB key, and splice loss at 0.1 dB key maximum in the final test. These aren't suggestions, they're hard requirements. It ensures that the network AtkinsRealis helps build for FDOT isn't just good on paper, it's proven excellent in the field as that built-in safety factor again.
Okay, wow. So pulling this all together for this deep dive, we've really unpacked the logic behind designing fiber networks, the backbones, distributions, drops. We've looked at how redundancy is built in, the practical ways fiber gets installed, like pulling versus blowing.
And critically, how it all gets tested, using tools like the OTDR to meet those very high FDOT standards, often engineered by firms like AtkinsRealis.
It feels like we've turned a lot of technical jargon, maybe word soup, into something much clearer. You get a real sense of the process now, especially with those real-world FDOT scenarios.
Hopefully, yeah.
Yeah.
You get a glimpse into the complex, precise work that goes into building this foundational layer for our transportation systems, work that AtkinsRealis does routinely for FDOT to keep Florida connected and moving safely.
It really is incredible, the amount of unseen effort involved.
The precision needed, especially at the FDOT level, is definitely impressive when you get down to it.
It makes you think. Given all this precision and these high standards for fiber networks that most people never see, what other essential invisible layers of infrastructure are underpinning our daily lives that we just, well, take for granted? Something to ponder.
Definitely. Maybe next time you're driving, notice the traffic cameras or message signs and give a little thought to the invisible threads of glass making it all work and the effort that went into putting them there.
Well, thank you for joining us on this detailed exploration. And remember, this deep dive into fiber optics was brought to you through the expertise of AtkinsRealis, developed in collaboration with the Florida Department of Transportation partners working together to build the robust communication backbone for our future.